So to give you an example, if you take a balloon that's shaped like a watermelon and you take an actual watermelon and you then drop them, of course, the balloon will fall slowly and the watermelon will fall faster. So this was an intuitive thinking by Aristotle. Of course, he didn't give you the equations that I showed you, but that was the way he portrayed physics back then. Then in 1638, until that time, no one challenged this idea. But in 1638, we know the story of Galileo, who climbed the Leaning Tower of Pisa and dropped two balls of the same size and different density. He tried this with various other balls of various sizes. And he found out that each time, both the balls fell with the same velocity. So the heavier one didn't fall faster, both of them fell together. Of course, this may be an anecdote because many people say that this really didn't happen, but his biographer was the one who first mentioned it. So Galileo said no, Aristotle was wrong. The story down the line goes on to 1679 when Isaac Newton, we all know him because of all the laws he has given us, gave out the laws of motion, where he said that F is not is equal to mv, it is F is equal to ma, which means force depends upon the acceleration. And this acceleration governs how fast an object falls. So we've all studied this equation over here, and this is known as one of the equations of motion. We've got three of them like that. And if you just substitute the right ingredients, you'll realize that the velocity of the body, how fast it falls down, has nothing to do with mass. There's no m over here. So this is what Newton said in his book, the Principles of Mathematical Philosophy, or Principia in short. Newton also gave out the very famous rule of gravitation, where he said that force is directly proportional to the true mass of the objects and the distance between them, inversely proportional to the square of the distance between them. So if you do a little bit of calculation, equate the second law of motion by Newton, and you equate these forces here and do some calculations like this, and you equate it to a gravitational potential, then what we'll get is that for every object of mass capital M, given universal gravitational constant g, at a specific distance r, you get an equation for velocity given by v is equal to root of 2gm by r square. What does this equation tell you is that it is the velocity required to escape the gravity of any given body. So if an object has mass m, then v is the velocity required to escape its gravitational pull. So v is the velocity. We'll remember this equation because we'll be using this further down. So just to give you an idea, whenever there's a huge planet, let's say a planet of this big size and capital M is its mass, and you've got a smaller object like a stone with a small m as its mass, then if you throw the stone upward with a velocity less than the escape velocity, then the stone will basically move up and come down. Whereas if you take a stone or a similar stone, or the same stone for that matter, and throw it with a velocity greater than the escape velocity, that is the velocity greater than that formula that I just mentioned, then that object will go out, escaping the gravitational pull of this planet. If we replace this planet with the planet Earth, and now for Earth, let's say we try this with the same stone, and for this planet that we live in, the equation that I just showed you gives us the escape velocity to be 11.2 kilometers per second, which means if I throw a stone up in the sky with a velocity of 11.2 kilometers per second, then it will escape Earth's gravitational pull. Now this makes us curious. What if it was on the sun? Because sun is a very huge body. We know its mass is very, very, very large. So for the sun, if we were to do this calculation, we would find out that the escape velocity for the sun would be 618 kilometers per second. And with this velocity, if you throw a stone from the surface of the sun, of course, not possible to stand on the surface, but just to give you an idea, if you throw a stone at 618 kilometers per second from the surface of the sun, then we would have the object escaping the velocity, the gravitation of the sun. Earth is not in this velocity, so we are still under the gravitational pull of the sun. Speaking of escape velocities and stars, the reason I've brought in the sun over here is because sun is a star and sun emits light. And back in Newton's days, Newton proposed this theory known as the corpuscular theory, on which John Michell was the first one to propose that if you consider light as a particle, then there may exist a star with the same density as that of the sun, which means the same material as that of the sun, but the diameter would be 500 times greater than the sun. Right? So the diameter of that star, if it is 500 times greater than the sun, then assuming that light is a small tiny particle with some finite mass, then with the same density as that of the sun, the corpuscular particle, that is light, would not be able to escape from the star, which means the light leaving the star would not reach us. This is very important because today all of the light that we receive from the sun leaves the sun and reaches us. So in 1783, John Michell gave the idea for dark stars. Later it was worked upon by Laplace, and if you work out the equations, you'll find out that you can relate the velocity with density in such a manner. I'll just skip through these equations quickly because they are just to show you what it kind of tells you. Let's go to the final equation. If you apply this equation with the sun's escape velocity, okay, you would get whatever I showed you the value, 618 kilometers per second. Now, if you replace the radius here with that of 500 times the sun's radius, density is same as the sun, and this radius is 500 times bigger, greater than the sun. So bigger star, then this calculation would lead us to the value 308738858 kilometers per second. Of course, when you look at this, you know it's close, I mean, it's greater than the speed of light. So this was the first idea put forward by John Michell, that there may be stars out there who may be so massive, but Michell spoke in terms of same density and bigger radius. He said that there may be such massive stars out there that their light will not escape their own gravity, and we will not be able to see such a star, because we see something when light is reflected off its surface or emitted by the surface and reaches our eye. So if the light does not reach our eye, does not leave the star, then there's no way we can see these stars. That is why we call them dark stars. Another development came in this theory of black holes in the form of Einstein's general theory of relativity, where Einstein said that gravity is an effect due to the bending of space-time, and the bending occurs because of mass, and this curvature, that is when space-time bends, this is what guides objects, waves, and everything else, even light, to move forward. So what appears to be moving in a straight line, like we know that light always moves in a straight line, may be through a curved space, and this curvature is formed by mass. This was the idea put forward by Einstein. He spoke nothing of black holes, and he published this in the year 1915 through his paper. And before I proceed further, I just used a term over here, space-time. When we study black holes, when you learn about black holes, we need to identify what space-time means. We need to understand what space-time means. So just to give you an idea what space-time means, imagine space is made up of all these points, right? So this is a three-dimensional space. All of us live in the space. Earth is located in the space. A galaxy is located in such a space. Now imagine that each of these points is like this unit cell that you see here. They're equidistant from the nearby dots, and they are not pulled or pushed or crammed or any such matter, in which case we call space-time to be a vacuum, or it's normal. Now the reason I'm calling this space-time, I'm including the word time here because Einstein said, of course we can imagine space like this. We are taught this in school, x-axis, y-axis, and z-axis, right? So we've got the x-axis, y-axis, and the z-axis. Anything that moves in day-to-day life, any movement can be described as the change in x, y, and z. But Einstein said, no, not just this. Imagine every single point in the space, time, to be having a clock. Now, time would also be a coordinate. So as you move forward in space-time, not only would your space coordinates change, not only would your x, y, z coordinates change, but also a time coordinate would change. Just to give you an idea quickly, if you're sitting wherever you're sitting right now listening to the webinar, you're not moving along the x-axis, you're not moving along the y-axis. I hope so, you're not flying. You're not moving along the z-axis, but you're moving along the time axis, because time is right now 6:17. In a while it becomes 6:18, 6:19. So you're moving forward in time. So this is how Einstein thought of space-time. Quite hard to imagine, but this is how we'll accept it. Using this concept of space-time, Einstein gave us the equations. These are called the GTR equations, or the Einstein's field equations, quite complex equations. So I'll not explain them in detail. But understand that the equation here on the left-hand side will tell you about the curvature of space-time, whatever he mentioned, space-time curves. And the equation on the right side gives you this P over here, tells you about the mass, the stress caused by some mass, the stress that leads to the curvature. So to put this into picture, because equations don't really make sense when you look at it in such form without understanding them, to put it into picture, space-time can be imagined as a fabric. Of course, it's in all three dimensions, not just one flat surface like this. On such a fabric, if you drop a mass, it will bend. So imagine space-time to be like a rubber sheet. On this sheet of space-time, if you drop a mass, an object of some mass, then that mass would bend the space-time. Now you can see in this image very clearly, the larger the object, more the bending, which is evident from this larger sphere over here. And then smaller sphere over here is causing a lesser bending, right? And whenever we say light moves in a straight line, it is basically moving in the space-time. So light always moves on this path of space-time, and if it is moving in a space-time that is not bent like this region over here, light will really move straight. And when light moves around these points here where it is curved, light appears to be moving straight to us from where we are observing, but it's actually moving in a curved path when you look at it from a very, very, very far point of view. Also, another point I'm missing over here is that mass bends space-time. It has nothing to do with the size, it is the mass. So two objects of the same size with different mass would bend space-time differently. We'll come back to this picture later on, but we'll just understand how space-time bends around masses. So you can see here in the right image, it's bent a little less compared to the image on the left, right? So two objects of the same radius, different mass, so densities are different, and this is what tells us how space-time bends. After Einstein published his work in 1915, Karl Swarzchild in 1916, while he was a soldier in World War I, did some calculations and found out that if the mass m is fit inside a very small radius, right? So if you take a little bit of mass, whatever is that mass, and you put it inside a small radius called RS, we call this the Schwarzschild radius, then it would bend the space-time into a curvature so intense that even light cannot escape. Light cannot escape. We are moving back to the idea of dark stars, where the space-time curvature is bent so that light will not leave the star. But before we jump into black holes and how they look and all that, how did Karl Schwarzschild reach there, and what did he use? Just to show you that these are not simply concepts that we imagine, because idea of black holes are very large in number, but the proof is very less. I need to tell you a little bit about the geometry. Just to give you a small idea, quickly let's go through the geometry of this. In school, we are taught that the distance between any two points can be given by three coordinate, the square of this. So the distance squared is dx squared plus dy squared plus dz squared. If I'm supposed to write this in the general form, right, this may be just three equations. This may be plus 0 plus 0 plus 0 or whatever equation, large equation there is. So if I write this equation in the most general form, I will get something like this. So from here, you can see I've got dx squared, which means dx dx. Okay, I've made a small mistake over here. It's dx dx, dy square is dy dy, and dz square is dz dz. And because this is just dz squared, I can assume that gzz is 1. We don't see any dy dz in this equation, so I can say gyz is 0 and so on and so forth. So if you do all these calculations, we can write this in a short form. I'll not explain this in detail. So you just replace a and b with xyz and sum it up, you'll get this bigger equation over here. And if you do that, you can write this G as some matrix known as, it's basically known as the metric, right? I'll not explain in detail. This is just the calculations we require to go end up with a black hole. So in spherical geometry, this comes in high school or maybe somewhere in PO or degree, we are talking about spherical geometry, where we are talking about not the x, y, z axis, but a spherical axis where we have got r, theta, and phi. So if you do the same calculation, distance between 2 points in such a geometry would give me such a large equation. And again, you've got dr squared over here. We've got dr, so this is dr squared. There's nothing multiplied over here, so grr is 1. Similarly, here I've got d theta squared, d theta, d theta. I've got an r squared over here, which means g theta theta is r squared, and so on and so forth. If I calculate this equation further, the same matrix will now become 1. Okay, another mistake here. This is r squared and r squared sine theta, sine square theta, right? I'll show this again in a while. So space-time, how does it change? How does space-time differ from space? What Einstein added to this idea of space that we had before. So Einstein said that space-time is a combination. It is not just space, but time again. So distance between 2 points, which we call events now, is the same dx, dy, dz, the square of these terms, plus a time coordinate added. So again, in the spherical calculations, we've got dr, and this d omega is basically theta and phi equations. We've got a time coordinate added. So along with the space coordinates, we add the time coordinate, and we get this whole metric tensor is what we call them. So earlier I showed you when it was just xyz, it was 1, 1, 1. Now dt squared is added. I'll add another row and column, and there's a c squared added over here. Okay, so I've added a c squared over here. Similarly, earlier I had got 1 r square sine square theta. This is that matrix over here. And to this, I've added c squared here because of the t squared. So these are all the calculations included for understanding space-time. It's not as easy as imagining a rubber sheet with mass dropped on it. But what Swarzchild did is known as the Swarzchild solution today. And he said that this G or this ds square equation can be written like this. Now you see that with r squared, it is not simply 1, but a whole term 1 minus rs by r and so on and so forth. You've got again for t term and all that. So now Swarzchild said that the metric can be written in such form. Too many complicated mathematics. Let me simplify it for you. What Swarzchild basically said is, I can define a radius r known as rs such that I can obtain this rs for any object of mass m by using this formula. So if you substitute mass m of that of sun or that of earth, g is the gravitational constant taught to us in school, c squared is the speed of light, which is again a constant. So for any given mass m, rs is defined. This is what Swarzchild told us. This leads us to the callback of Newton's equation, where I showed you very early that the velocity, escape velocity for any mass can be given in such an equation. If I square the equation, I'll get so and so. Now this is the escape velocity equation. And if I somehow imagine an object on whom the velocity to escape the gravitational pull is that of the speed of light. So if v, that is escape velocity, is equal to c, then I'll get c squared is equal to 2gm by r, or r is equal to 2gm by c squared. In the previous equation I just showed you, rs is equal to 2gm by c squared. So these two equations are the same. So what does the Swarzchild radius tell you? Swarzchild radius is that radius inside which you need to fit the mass m, however big it is, such that on that object or on that sphere of radius rs, the velocity to escape the gravitational pull would be equal to the speed of light. And Einstein told in his theory of relativity that nothing can move the velocity of light. So coming back to the bending of space-time, we've got the space-time curvature for two different masses. Now we've got two masses of different density, or two objects of the same size but different mass, we can say. The curvature bends differently for them, I told you. This has nothing to do with the size of the object, is what I told you. So now, if we consider this for a heavier object of smaller size, denser object, like the sun may be bent. Someone has unmuted their mic. Okay. Yeah. So we've got a star, let's say, of some size, and its density is less compared to the blue star over here. Then the space-time would bend much more for this denser star. So similarly, what would be the space-time curvature for a Schwarzschild radius? Of course, this image ends over here because this would never have a bottom. We call this a singularity, but I'll come to the singularity later. A Schwarzschild radius is that radius inside which an object of mass m can be fit inside, such that the velocity to escape that gravitational pull would be equal to the speed of light. Can sun be a black hole? Yes, of course. If you substitute the equation with the mass of the sun, then m is equal to 1.989 into 10 power 30 kg and so on and so forth. You do this whole calculation, you'll get that if you fit the entire mass of the sun, 1.989 into 10 power 30 kgs, into a sphere of 2.95 kilometers, very small, then the sun would become a black hole. You can also do this for Earth. If you substitute Earth's mass, then you would get that at a radius of 8.86 into 10 power minus 3 meters, that's 8 millimeters, less than 1 centimeter. If you compress all of Earth's mass into this small size of 9 millimeters, a little smaller than 9 millimeters, then Earth would also become a black hole. So we've understood what black hole means now. We've understood the calculations for a black hole. Where do we find black holes? How are they formed? These are the questions that come. So the birth of a black hole would be the same as the birth of all of us. The associating of this program, Particular Regional Science Center, had this show called We Are All Stars, which is a beautiful show that tells us that all of us are product of stars. Stars that go supernova lead to various elements that makes up all of the things that we know, all of the things that we are. Similarly, a black hole is also formed using a star's death. A star will have multiple stages in its life, and a sun-like star will end up like a red giant and soon a white dwarf in some day. But a really giant star, it's a blue supergiant, when it is towards the end of its life cycle, it will explode into a supernova, and at the end of this explosion, depending upon the mass of the star that is governed by the Chandrasekhar limit, the star will either become a neutron star or a black hole. So this is how black holes are formed. If a star's mass is around 8 times the solar mass, that is, if a star has the mass that is 8 times the solar mass, the sun's mass, then the supernova explosion will lead into a black hole. So now that we know the space-time curvature for heavier objects, denser objects, for black hole, we would have a space-time curvature like this. So for the sun, you would have a curvature of such nature. A white dwarf, which is much more denser than the sun, would have a steeper bending. A neutron star, which also comes from a supernova, will have a very steep bending, very strong gravitational pull, we would call it. And for a black hole, we would have a curvature or a bending of space-time that goes up to infinity. Thus, going to infinity leads to the concept of singularity. And we've also got the term event horizon. Somewhere down the line, we've got the last stable orbit for a black hole. So let's understand each of these terms one by one. So as we talk about singularity, we will lead to scientist Roger Penrose, who in 1964 proposed that black holes contain singularities within them. So what is a singularity? Mathematically speaking, singularity would be a point of infinity. So inside one single point, if you had infinite gravity, infinite temperature, infinite whatever property it is, it would be known as a singularity. So Roger Penrose, he won the Nobel Prize last year for the same discovery, known as the singularities theorem, theorems of singularity, which he proposed around a black hole that tell us today that at the heart of every single black hole, there is a singularity. Singularity means that it is a point of infinite gravity. That is why light cannot escape it. Nothing can escape it. Light cannot escape it. Nothing can escape a black hole. So what types of black holes are there? We can categorize black holes in terms of their sizes. We've got basically 4 types of black holes. A micro black hole, which was recently proposed when the CERN Super Collider opened. These are very small subatomic size of black holes. We have not discovered them yet. We've got stellar black hole, a lone circle. That is the photon sphere itself. And the event horizon lies inside this black hole. So moving on further, if a black hole, a static black hole is charged, then along photon sphere, of course, it has no angular momentum because it is not rotating, it is static, but there is a non-zero charge to this black hole. What you'll observe is the event horizon is now split into 2. You've got the general event horizon, which we spoke about in the previous, the uncharged static black hole. The same event horizon exists here as well. And inside this event horizon, we have the Cauchy's horizon. Cauchy's horizon is what gives headache to mathematicians, because once an object enters a Cauchy's horizon, then even the mathematical equations cannot predict what it's going to be. Of course, once it reaches singularities, it is undefined. But even before, once an object crosses the Cauchy's horizon, an object cannot be deterministic, is what we say. Or to put it in simple terms, I cannot tell you what is going to happen to the object. So rotating black holes, once we're done with static, the rotating black holes will have 2 photon sphere, one for photons that are going around the black hole, along the rotation, and one for photons that are going against the rotation of the black hole. So the black hole may be rotating counterclockwise and the photon may be rotating clockwise. That is the purple circle over here, and the blue circle that you see is when the photon is going along the black hole's rotation. Such black holes have an angular momentum, it has got two photon sphere, and it has also got an ergosphere. An ergosphere is that point where a photon cannot stand still. So this is that point where we say everything becomes unstable and will eventually fall into the event horizon. Depending upon the charge of the rotating black hole, we may have one event horizon or two event horizon. And of course, at the center of all these black holes, we've got the singularity. So what happens when a matter comes close to the black holes? What happens when matter falls into black holes? In such case, when a matter falls into black holes, all the properties, all the physical properties are swallowed. Of course, the matter itself is swallowed by the black hole. Along with it, all of its properties are swallowed by the singularity. And what happens to the information of these properties, we don't know. Of course, when we say swallowing, a black hole can swallow a lot of matter and hence grow in size. So black holes may be able to swallow an amount of numerous amount of matter in terms of interstellar dust, in terms of star, and so on and so forth. A black hole may grow by swallowing this matter. But in spite of swallowing all of these matter, in spite of, when I say matter, of course, that matter has a temperature, that matter has charge, that matter has angular momentum, that will have so many properties, yet we have the no-hair theorem. No-hair theorem about the black hole says that only information about the black hole that we can read is the rotation that is given by J, the charge that is given by Q, the mass of the black hole is the three objects, are the three properties that are readable, and no other information. So here is a metaphor saying that no property, or there is nothing to a black hole other than these three properties, not even hair, that we can read or identify. So this is why we have got the no-hair theorem. Information swallowed by the black hole, like I told you, cannot be read. So all information is lost. Here comes the great guy who's contributed to black hole calculations, that is Stephen Hawking. In the year 1970, he said that just like the laws of thermodynamics, just like in thermodynamics, we've got the law of entropy, the second law, black holes also need to have certain laws for them to exist. So we've got the black hole mechanics, or the laws of black hole, which Hawking worked with other scientists to give us. The zeroth law says that the surface gravity of a black hole is a constant. Of course, gravity does not vary along a black hole, which is easy. The second equation says that energy of a black hole is governed by only these properties. You see here, A is the area of the black hole. Of course, area of the black hole, I told you the black hole may grow in size. J is the rotation of the black hole, its angular momentum, and Q is the charge of the black hole. So energy of the black hole is given by just these three properties. The second law is very important here. It says that the rate of change of area with respect to time is always greater than zero or equal to zero, which means a black hole will always grow in size. And the final law tells you that you will never find a black hole that will have no surface gravity. Of course, black hole comes from the idea that even light can't escape it. So every single object in this universe will be having certain attraction towards the black hole, and it will be swallowed by the black hole. So once you consider these laws, Hawking gave us this equation that tells us about the entropy of a black hole. Just to tell you that entropy is what governs the universe. Entropy is what tells us why time cannot move forward and back, right? We always move we always move in time forward. We can never go back in time. There's no time travel in backwards direction. That all of that is because of entropy. And Hawking said that even black holes will have entropy, which can be determined using this equation over here. And you see in this equation, all are constants. K is the Boltzmann constant, C is the speed of light, G is the gravitational constant, and H cross is a constant. So A is nothing but the area. So the area of the black hole determines its entropy. And Hawking also said this beautiful concept known as the Hawking radiation. He said that very close to the event horizon, pairs of particles are created. Of these pairs, one is a real particle, one is a virtual particle. We call this the antiparticle. And these are created very close to the black hole. And once these are created near the black hole, one of them may be absorbed and the other one will escape. If they're not absorbed, as shown in this image over here, if they're not absorbed, they will meet with each other and annihilate, or basically disappear. So these particles appear out of nowhere and they disappear also out of nowhere. But by chance, if the negative one is absorbed by the black hole, the positive one will escape the pull of the black hole. Then we can see a kind of radiation coming from the black hole. So this is an animation that tells you the arrow marks are for the particles that are separated, and one gets into the event horizon and another one escapes. Here you can see particles are created and they are destroyed as well. See, particle created and destroyed as well. So this is Hawking radiation. This leads us to the idea of the information paradox. This is what Hawking asked us. If everything is absorbed by the black hole, if all matter is swallowed by the black hole, where is the information? This leads us into the domain of quantum mechanics. This will make black hole calculations more complicated. So this is where I'll basically stop explaining the physics of the black hole. But the information paradox tells us that information that goes inside a black hole is lost forever. And only these properties, mass, electric charge, and angular momentum, is what we see or what we observe. The rest of it is lost. But this should not happen. Information cannot be lost inside a black hole for the universe to be normal. So idea of this was given by the holographic principle, but this today again is not very relevant. But the holographic principle says that everything that falls into a black hole, its information, its properties are somewhere stored on the event horizon. The entire two-dimensional surface, the sphere of the black hole, stores all the information about this three-dimensional world. Like you can see over here, the sticker. This is a sticker known as the holograph. Inside the sticker, when you move the sticker and the light reflects off it, you can see as if the 3D font written on it moves. Similarly, this is an image of basically a video of a holograph generated. You see the butterfly is basically a two-dimensional image. You've got 4 butterflies on a two-dimensional surface. And when you compile it, when you put it together to project it properly, you can see a 3-dimensional butterfly projected. So the holographic principle says that all the information swallowed by the black hole is embedded on the surface of the black hole. I will basically stop talking about the physics of the black hole at this point, because from this point on, it becomes complicated and unsolved. So further down the line, how do we see black holes? Seeing black holes is difficult because I told you they don't emit light. We see things when light is reflected off a surface or emitted by a surface and reaches our eyes. But black holes don't do that. So how do we see them? Of course, if two black holes merge, because we have spoken about space-time, whenever two black holes come close to each other, they can come closer and closer and closer. Of course, they've got a gravitational pull, and you can see in this image here, they can combine. So when such kind of a case happens, when black holes merge, space-time is disturbed, which leads us to gravitational waves, a very promising area today. And we measure these gravitational waves on Earth using the light interferometer gravitational wave observatory, which is basically LIGO. There are 2 such observatories with laser beams that span almost 4 kilometers long. 2 of these are located in the United States, and 1 is being planned in India as well. So how do these work? Basically, when no wave is detected, no gravitational wave is detected, light is normal. But when gravitational wave is detected, of course, space-time expands. And when space expands, the distance between the mirrors will move, and therefore we will notice a small change. And we've already discovered gravitational waves. And almost a year back, we had news where scientists had discovered merging of a black hole using gravitational waves. So gravitational waves is a method for us to detect black holes without even seeing them. Another assumption that we can do is all the stars in our galaxy are held together. All the stars in the Andromeda galaxy are held together. How are they held together? There has to be something that is pulling them together. This is an image of the stars at the center of our Milky Way galaxy. You see the stars of this region are moving very fast. And when you do the computer simulations of these stars, taking the data, you see that we have drawn a star over here, which is basically a blank space in the image. And all the stars around it are moving as if this is a computer simulation of how we will see the accretion disks. Of course, how do we see the accretion disk? Because once we see it's a disk, what if I see a disk from a point of view so that I see it from the side? We've got computer simulation that tells us how they'll appear. And further down the line, because of these accretion disks, we've got the concept of quasars. Whenever a black hole is absorbing a lot of matter together, this matter cramps together near the event horizon, and so much traffic is there that matter has to escape somewhere, and this escapes in the form of these beams that you see over here. right? These vertical beams that you see are known as quasars. So here's a galaxy, the M87 galaxy, here at the center, and this was a decade-old photo, and you see a beam of quasar over here. So quasars can be detected, and once you know there's a beam of electromagnetic radiation, X-rays more primarily, then we know that these quasars are because there's a black hole at the center. This galaxy is the Centaurus A galaxy, which is also being studied, and this galaxy has also exhibited these quasars. M87, later down the years, once Hubble captured it in more detail, we found out that the quasar from M87 is really, really, really large. You see, this entire glow region here is a is the galaxy. You've got stars so haze. This is and created this video image of this quasar moving forward. These quasars are so long that they even span the length of the galaxy, perpendicular to the plane of the galaxy as well. Another way of detecting black holes is gravitational lensing. Like I along this space-time. So a curved space-time will also curve the path of light, such that light coming from behind a black hole will always form a curved path so that we can detect them. Here's an image I told you about the star cluster seen to us in the form like it looks like Saturn with its rings, right? So this is how we can expect to see a black hole once we can capture an image of a black hole. So how do we capture an image of a black hole? Of course, visible light, not possible. Black hole does not emit any light. And they are so far away that we can't have any strong telescopes that can detect visible light from a black hole. So in such a endeavor, several telescopes across the Earth came together and formed the Event Horizon Telescope. You can see there are multiple observatories, radio observatories basically. Even from the South Pole, you have an observatory, such that they combined together, they switched on all their telescopes together at the same time and acted like one giant big telescope. You can say that this disk of the Earth itself is the aperture of the black hole. I'm sorry, aperture of the telescope, right? Sorry. So this itself is the size of the telescope. Like in our college and our schools, we say 8-inch telescope, 10-inch telescope. The Event Horizon Telescope is the size of the Earth. And once we started this collaboration in the Event Horizon Telescope, we started imaging the M87 galaxy that I showed you a while ago with that quasar coming out of it. And from 2009 to 2017, they took images of this black hole, and slowly and steadily, one by one, as the observatories collaborated and captured more and more images, in 2017, they released this image. So this was the galaxy that we saw in visible light, and this was the center of the galaxy that we saw with X-rays and radio waves. And this was the image we found in 2017. This is the first image of a black hole that is at the center of Messier 87 galaxy. And last year, they added a small data. Of course, the black hole does not look like this. This is an interpretation of the radio data. Okay, radio telescope observe radio waves, not visible light. So you would not see a black hole. They've just converted the data to assume that it may look like this. And last year, they gave us this image saying that if the black hole has a charge and it's spinning, it will have some magnetic field as well. And these lines here identify the magnetic field because of the polarization of the black hole. And as we talk about black holes, the largest ever black holes detected is the OJ287. This is a black hole that has a smaller black hole orbiting it through its accretion disk, which is very, very, very beautiful. The smaller black hole itself is 100 million solar masses, and OJ287 is 18 billion solar masses. Just to give you an idea, if you put OJ287 at the center of our solar system, of course, center of our solar system would be wrong, because the entire solar system would be just a small area inside OJ287. And the smaller black hole I told you will fit almost up to the orbit of Mars. So these are the sizes of black holes you've discovered. And before I conclude this session, when you go down the line about study of black holes, we will come across the concept of white holes. Just like black means no information, white means all information. White holes are hypothetical concepts that may be the opposite of a black hole, which says that just like light cannot escape a black hole, there may be a phenomenon known as a white hole inside which light cannot enter. So a white hole is a hypothetical concept. Maybe somewhere people say this may be the Big Bang and so on and so forth, but we have only one image of a black hole so far and only a few measurements of various other black hole mergers and so on and so forth. So the information we have is very, very, very small and very small in number. So I hope I've answered many questions about black holes that you guys had. Thank you so much. Thank you everyone for the opportunity you provided me to share my ideas.
Thank you, sir. We will go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the question box in your control panel. You may also ask questions directly by turning audio on. It looks like we have few questions. Question is from Harisha Archer. Is there any new knowledge on Chandrasekhar limit?
The Chandrasekhar limit was calculated by Subramaniam Chandrasekhar, and we know it's 1.44 times the solar mass, and it's quite well defined. So all we can do now is identify what kind of stars lead into a black hole and not, and so on and so forth. So not much knowledge is obtained from Chandrasekhar limit because most of it has been given to us in proper details and research over the span of decades.
So another question, is there any relationship between God particle and inside of a black hole?
I mentioned that the center of a black hole is a singularity. So when I say singularity, I don't know about it. No one knows about it. Even the scientists studying it don't know about it. Even Roger Penrose himself does not know about it. So identifying or understanding if there is God particle in the singularity, probably not, because God particle is just a name given to a normal matter, and it is known as the Higgs boson, which exists in our universe itself. So it's outside the black hole that it exists. We have detected this in the CERN super collider. So inside the black hole is there what is it, God particle? I don't think that question actually fits in there. Inside the black hole, we've got singularity, and nobody knows what exists at this point.
Sir, another question. What is a way to connect to other world through the present? Scientists believe.
I'm not sure what you mean by when you say other worlds, because I told you I stopped at a particular point with the black holes because I explained about black holes from astronomy point of view, astrophysics point of view. And if you go further down from the point where I spoke about Hawking radiation, it becomes a quantum mechanics problems. And all particles are very, very, very small in this case. And once you get into quantum mechanics, you've got multiverse, you've got many universes, and so on and so forth. So far, we don't know. Of course, movies tell you that if you jump into a black hole, you lead to a multiverse and so on and so forth. But physics does not tell us anything about other universes through a black hole.
What is a black hole and space-time? In simple terms, where black holes find, and what about white holes? Question
Yeah,
asked
so
by Akshit Acharya.
yeah, so I've basically answered this question. Black hole is basically an object from which light cannot escape. Space-time is everywhere around you. Space that you see is basically space-time. And then white holes, I told you, they are just on paper, just equations that say that maybe if you reverse the process of a black hole, you'll get a white hole. We have not detected any of it yet.
What is the name and distance to the nearest black hole?
Nearest black hole, I'm not aware of this fact. You can just Google it, I guess. I'm not really sure the nearest black hole that I can think of. But the most studied and the nearest black hole that we can think of is the center of our galaxy itself, the Sagittarius A star that I showed you. We don't know it exists because you can see it. We know it exists because of the stars around it. So we know the properties of this. Of course, along with Roger Penrose, the two other people who got the Nobel Prize was for the discovery of that black hole itself. And that is the closest black hole that we know, that we have studied well. But there may be a black hole lurking around outside our solar system, very small one, a micro black hole perhaps, but we don't know about it.
Sir, another question. There is a black hole in the center of Milky Way galaxy.
Yes, that's what I just said. The Sagittarius A star is a black hole. When you look at the night sky, once Sagittarius constellation is out, you will see that you see a band of white patch in the night sky. That is our galactic plane. That is our galaxy and all the stars that are there in our galactic plane. And at the center of this is a black hole, is what we believe. And we've got enough data to say that there is a black hole there. Of course, it's been proved. That's why they gave the Nobel Prize last year to these scientists. So there is a black hole at the center of our galaxy and also many other galaxies. Like I told you, M87, the Centaurus A, these are all galaxies with black holes. Almost all spiraling black holes, all spiraling galaxies are believed to have a black hole at their center. That is why all the stars are spiraling towards the center.
Difference between quasar and a neutron star.
Uh, Neutron star is basically a brother to a black hole. I told you a supernova may end up either in a neutron star or a black hole, depending upon the mass of the star. Quasar is basically a burp that the black hole takes, because after we all eat, we usually let out a burp. So even the black hole, when it is eating a lot of mass from a star, it is giving out a burp in the form of a quasar. So quasar is a property, is basically a phenomenon coming from a black hole, and a neutron star is basically a brother to a black hole. It is another way a star could end. You may be asking about pulsars, which is basically a neutron star that is giving out light into space, which is very close to what a quasar looks like. But again, very close, but two different phenomena.
What is the speed of light in a black hole?
Speed of light is the same everywhere, but inside a black hole, even that is useless. Speed of light inside a black hole is c, that is 3 into 10 power 8 meters per second. But event horizon is not going to let you come out of it, even with that speed.
So what part of the electromagnetic spectrum does Hawking radiation dominate?
Okay, so Hawking radiation is not particularly from the electromagnetic spectrum. In the electromagnetic spectrum, we have got photons coming out. These are basically X-rays, gamma rays, basically microwaves, radio waves, and so on and so forth. Black holes do emit radiation in the form of the accretion disk, not the black hole exactly. The accretion disk and the quasars emit X-rays. But Hawking radiation in itself is basically two particles, maybe an electron and a positron, maybe a proton and an antiproton. So Hawking just said that quantum mechanics tells us that there are particles. We have not even seen them in reality. Hawking only told us that if you've got the right conditions near the event horizon, you've got a condition where two particles, a proton and an antiproton, or an electron and a positron, may be created and they'll go and annihilate themselves. May be created somewhere else and annihilate themselves somewhere later. So maybe one of them is absorbed and then the other one will reach us someday and become Hawking radiation. So it is not electromagnetic radiation.
Great. Thank you, sir. It looks like we have covered all of your questions. Thank you, sir, for the wonderful presentation. Participants, please note, feedback link will be shared in a Google Meet chat box as well as in YouTube chat at the last 5 minutes of the session. Certificate will be provided to the participants who submit feedback forms every day. Now, I would like to request Professor M. Ramesh Bhatt, convener of Amateur Astronomers Club, to speak on this occasion.
Good evening to everybody. Congratulations to Mr. Atul Bhatt for your wonderful presentation. You have given a lot of information about black holes in the limited time allotted. Interaction session was also very interesting. Thank you. I request all the participants to join us for 4 more days of the webinar, in which there are more interesting topics which can be understood even by high school students and general public. And those who have not joined our WhatsApp group, please join. And also those who have joined, please continue so that you can get a lot of information from our WhatsApp group also. Thank you.
Thank you, sir. By this, we have come to the end of this wonderful session. I extend heartfelt thanks to the dynamic personality, Mr. Atul Bhatt, and also Dr. K.V. Rao, Director of Pilkula Regional Science Center, Mangalore, Dr. Radhakrishna Shetty, Principal of Sri Mahavira First Grade College, Mudugidri, Professor M. Ramesh Bhatt, Convener of Amateur Astronomers Club, Mrs. Nalini, Mr. Harish H., Professor Harish, Mrs. Shweta, and all the participants who participated actively in this wonderful session. Participants, please note, tomorrow's session will begin at sharp 6 p.m. Resource person of tomorrow's session will be Dr. B.R. Guru Prasad, scientist, science communicator, and public relation professional, former Associate Director, ISRO. He will speak on the topic Mangalyaan. And we look forward for your active participation in the coming session also. Thank you one and all. Good night.
Thank you everyone.
Thank you, Atul Bhatte.
Thank
Nice
you.
presentation.
Thank you, sir.
Well done.